You know, sometimes the silliest, most ridiculous sounding questions can lead you to some truly fascinating places. So today, we're going to take a couple of those seemingly absurd questions and give them the full scientific treatment, just to see what we can learn about the world.
So let's dive right in. We're going to throw some real physics, real biology, and real world logistics at these scenarios, no matter how wild they seem. And trust me, you're going to be surprised by what these thought experiments show us about how things actually work. And here it is, our first big question. Yeah, you heard that right. Forget solar panels, forget wind turbines. Today, we're looking into jellyfish. Can these gelatinous blobs power one of the largest, most energy-hungry cities on the entire planet? This is going to be fun. Okay, so before we can even start designing our jellyfish power plant, we have to get a handle on the sheer scale of the problem. I mean, just how much power does a megacity like Tokyo actually need? The number? Well, it's pretty mind-boggling. 280 terawatt hours. That is the amount of electricity Tokyo burns through every single year. To give you some perspective, that is more power than the entire country of Australia uses. So, yeah, we're going to need a lot of jellyfish. So what kind of jellyfish are we going to use? Well, allow me to introduce you to our candidate, the Numera jellyfish. These things are absolute units. They can weigh as much as a piano, grow up to 2 meters wide, and have about 1,000 tentacles. And the best part? Their populations have been exploding lately, so, we've got a steady supply. But there's a tiny problem. Jellyfish don't exactly glow in the dark. And despite their sting, they're not really electric in the way we need. So how in the world do we get power out of them? Well, the plan is kind of brilliant in its simplicity. We're literally going to squeeze the power out of them. And this is the secret sauce to our whole plan. It's this really cool phenomenon called piezoelectricity. Basically, it means that when you put certain materials, like a crystal, under physical stress, you squeeze them, you bend them, they generate an electric charge. So here's how it works. In a crystal, normally all the atoms and their charges are perfectly balanced out. But then, when you squeeze it, you physically push that structure out of alignment. That forces the positive and negative charges to separate, creating a voltage. And boom, just like that, you've created a tiny little battery. And this isn't just some weird science experiment either. This tech is all around us. It's what makes sonar work. It's the magic that keeps time in a quartz watch. And heck, some net clubs have even built dance floors that generate electricity from people dancing. Pretty cool, right? Okay, so here's the master plan. We engineer these tiny, high-tech wetsuits for each and every one of our jellyfish's 1,000 tentacles. These little suits are made from a special piezoelectric material. So every time a tentacle wiggles or contracts, it bends the suit, and that generates a little spark of electricity. So after all that incredible, slightly bonkers engineering, how much power does one of our high-tech jellyfish actually generate? Well, about 10 kilowatt hours per year, which is enough to run your laptop for maybe 20 days. It's a start, but it's not quite lighting up Tokyo, is it? Right. So one jellyfish isn't going to cut it. Neither is 1,000, or even 1,000,000. The question is, just how many of these piano-sized wetsuit-wearing sea creatures do we actually need to meet Tokyo's insane energy demand? We would need 29 billion of them. No, that is not a typo. 29 billion Nomura jellyfish, each one fitted with 1,000 piezoelectric tentacle suits. The scale of this project just went from ambitious to, well, completely insane. It's hard to even wrap your head around a number like 29 billion, so let's try to put it in perspective. Right now on planet Earth, there are about 27 billion chickens. So to power Tokyo, we would need more jellyfish than there are chickens on the entire planet. And this is where the plan just becomes a logistical nightmare. I mean, to feed this army of jellies, we'd basically have to hoover up all the plankton in the Pacific Ocean. We need a storage tank 7 times the volume of Mount Fuji just to hold them. And we'd have to insulate 29 trillion individual tentacles. It's just not going to happen. All right, for our next question, let's get out of the ocean and look up at the sky. What if, for just one day, it rained bananas instead of water? At first glance, that sounds amazing, right? A global shower of free food for everyone? So let's start with the good news. If we took the average daily rainfall and just swapped it out for bananas, the planet would be showered in 1.2 quintillion calories. That's a 1 with 18 zeros after it. It's a truly enormous amount of energy. Think about that. Just one single day of banana rain could completely solve world hunger for over a century. No more starvation. Just a never-ending supply of potassium-rich goodness falling right out of the sky. It sounds like a perfect utopia.
So, what could possibly be wrong with a plan that feeds the entire world for 100 years? Well, as it turns out, pretty much everything. The problem isn't the bananas themselves. It's how they get here. See, a single banana falling from cloud height would be accelerating the whole way down, hitting a speed of over 240 meters per second. By the time it hits you, it would have the same impact energy as a bowling ball dropped from a 50-meter building. And that's just one banana.
This would not be a gentle fruit shower. It would be an absolute apocalypse, a shower of yellow death. Cities would be pummeled, roofs, windows, everything shattered. All our infrastructure would be wrecked and clogged with a planet-wide banana smoothie. The world's coastlines just choked with a thick sludge of trillions of rotting bananas.
And just like our jellyfish power plant, the initial disaster is really only the beginning. The real catastrophe would start after the banana rain stops, when all 1.3 trillion tons of fruit just starts to rot. As all of those bananas decompose, they would release a truly staggering amount of methane, which is a super potent greenhouse gas. We're talking 280 times our current annual global emissions, all at once. The result would be a sudden, catastrophic spike in global temperature, almost certainly triggering a mass extinction of. So why even bother with these crazy scenarios? Well, because they force us to really look at our world in a new way. They teach us about the laws of physics, the mind-boggling scale of our energy needs, and the incredibly delicate balance of our ecosystem. By asking silly questions, we stumble upon some very serious truths. And really, isn't that what being curious is all about?